Alright, it's time to talk some surface area of solids. Now, when would that ever come up? I don't know. How about on a house? Or a shed? Or anything in real life because it's 3D? Awesome. So let's talk surface area of prisms. And I'm going to try to go a little quick here so we can make it through these and get to those fun application problems. Okay, prisms, surface area. All we are doing is adding up the surfaces. So that's basically it. I'm not going to remember a special formula. You already have all these formulas. Let's think about what these things are made of. If you're looking at a rectangular prism, which is what we have up here, I've got a bunch of rectangles or potentially squares, depending on what I'm dealing with. If I look down here, I've got what's called a triangular prism because my two bases are triangles. So I've got two triangles and I've got three rectangles. Alright? Now all three of those rectangles may or may not be the same, pending on whether or not we have equilateral triangles. Or maybe we have isosceles triangles, where only two of the sides are congruent. Some we'll get into a little bit more later. Okay, or maybe it's a scalene, which means it has no congruent sides. All three of them are different. Oh my gosh! Okay, well, for now I'm going to give you guys some measurements for these two different problems. Let's say I've got, how about 6 feet for this base right here of that triangle. And let's say I've got this guy here is, how about 14 feet? Okay. And remember, the two triangles are going to be the same in a prism. Okay, we know that. With prisms, the bases are the same. They're congruent. And then let's say I've got this height. Of course, it's perpendicular if it's a height. Let's say this guy here is going to be 4 feet. Okay. Alright. And we are saying that this is an isosceles triangle. I'm going to say that too. Okay. So let's see what we got here. Well, if I'm going to find the area of my triangle, area of the triangle, I'm going to notate it that way for my work. Keep it all organized. Let's see here. Base times height divided by 2. So 6 times 4 over 2. That's going to give me, well, 24 over 2 is 12. And if I've got the area of the triangles times 2, I'm going to get 24 feet squared. Oh, almost got that there. Okay, there we go. That's good enough. Cool. So the two triangles is 24 feet squared. That'll be helpful in a little bit once I get my rectangles. Well, I got that bottom rectangle is 14 by 6. So one of the rectangles is 14 times 6. So let's see here. Well, 10 times 6 is 60. Plus 24, that is 84. And it helps to be good at some mental math here, kids. Because when you're out on the job site, pulling out that calculator every single time. If I'm always busting out my TI-84, that's going to be a whole big pain in the butt, don't you think? I'm not going to lug that around everywhere. That's going to be too much. Okay, so let's think about the other two rectangles we have there. This is actually something we haven't learned yet. Since this is isosceles, this is going to be 3 feet down there. Just this half right there that I outlined in blue. It's called a 3, 4, and then that hypotenuse there, another word we don't really know too well, maybe you know it, is 5. 3, 4, 5 triangle. So what I have for my other two rectangles, if you see that there, is a 14 by 5. Instead of by 6. Alright. So now what I have is an 80 square foot rectangle, and I've got two of those, so that's 160 feet squared for the other two. So if I take all my boxed stuff, because those are all my finals, right? If I take those guys, I got my 24 plus my 84 plus my 160, I'm going to get 268 feet squared. That is my total. Awesome. I'm going to outline it twice. Woo! Final answer. 268. So the big thing here, guys, is we don't necessarily need to remember a whole new set of formulas when we're dealing with three-dimensional shapes. We're adding in a bunch of our two-dimensional shapes. Altogether, we just have to be able to identify what's what. Okay? Okay, so what we have here is a square pyramid. Alright, and I'm just going to say it's a square, so I'm going to say all of these sides are indeed congruent. Okay? And in a square pyramid, you know what's awesome? All four of these triangles are exactly the same. My goodness. How wonderful. So, what do we have to do for our square pyramid formula? Well, again, we're just adding up the sides. There's no special formula here, guys. Let's say that this one here is 10 meters. So this is 10 meters. And maybe I'll give you this awesome slant height that goes perpendicular to that base. Let's say that that guy there is 12 meters. Okay. Well, can I figure out my total surface area? Area of the base, area of that base. It's be a 10 by 10. That's 100 meters squared. Easy. Done with that one. How about area of one of my triangles? I know the area of a triangle. Area of one of those triangle sides. Well, that's going to be base 10, height 12 over 2, 60 meters squared. And how many of those do I have? 4. 60 times 4 equals 240 meters squared. So what's my final answer? Well, if I've got my 4 triangles and my 1 square base, I'm going to have 340 meters squared for my entire surface area. Here's the thing though, guys. Sometimes we're not dealing with that base. Sometimes we're not dealing with every single side. You have to look at it and decide what you actually need the surface of. If this square pyramid were the top of a roof, right? If we were dealing with that as like the top of a roof, you wouldn't be dealing with this. That'd be on the inside of the building. We wouldn't need that base. So you got to look out and make sure that you're adding up what is actually part of the surface when you're talking about surface area. Alright, so it's time to get tricky. We got a cylinder here. Got like a soup can or a pop can, you know, or a garbage can, whatever. So with the cylinder, we've got our radius. You know, we got our radius like usual because, hey, look at that. We've got ourselves a circular base. That is a circle in 3 dimensions, so it kind of looks ovally. And then we've got a height. Want to guess what happens when the height, or what relationship the height has with the radius? Oh snap, they're perpendicular. Height is perpendicular to the circular base. How convenient. Now, what's the formula for the surface area? Well, you know what I can tell you right now, I'm pretty sure from looking at this, is since I got 2 circles, well, the circle, area of a circle is going to equal pi r squared, right? And there's 2 of them, so I'm going to multiply that by 2, so really like 2 pi r squared. I don't like to think about it like that, though, because sometimes I confuse that with circumference, but there are 2 circles, right? There's 2 circles, pi r squared, so 2 of them together. Okay. Well, what about that part that wraps around? It wraps around the circles. What the heck kind of shape is that? I wonder. Ooh. Well, here's another way of looking at it. As I said, a soup can is a cylinder. That label is wrapped around said soup can. What kind of shape is that label? Oh, I think I know this one. I feel like we've done this one. And I just, rectangle. Okay, a rectangle. Now, if we remember back to the last problem, we had this kind of like back part of the circle. There we go. So there's our circle base, kinda. We got our center. We got a height that comes up to the center, and that radius pops off of that, right? So the height of that label is the height of the cylinder. that base. What's this base equal to? Because I know the area of a rectangle is equal to the base times the height, but if only I knew what that base was. Because I got the height. I know what the height is going to be. If I'm given the height, I got it. What could that base be? Oh, snap. It wraps around the circle bases. The base is equal to the circumference, which is 2 pi r. 2 times pi times r. It equals the circumference of that circle. Excellent. Wonderful. So, let's add some values to a random cylinder, shall we? Okay. Let's say that my radius is going to be 3 centimeters, and the height is going to be 4 centimeters. Wonderful. Okay, so my area of my base is, so base area is going to equal pi times my radius squared. So that's 9 pi. And I got 2 of those, right? 2 times the base. It's going to equal 18 pi. Awesome. So that's one part of it. Now I need my lateral area. That's what we'll call it. The lateral area is the area that wraps around that cylinder. So let's do that lateral area. Lateral area is equal to the base, which remember is our circumference. So 2 times pi times my radius of 3 times my height, which is 4. I do like to use parentheses when I'm substituting. I think that's good practice. So my let's see here, we got 3 times 4 is 12 times 2 is 24 pi. Woo! Wonderful. So there's my lateral area. Now if I add up my 2 bases, which is 18 pi, and my 24 pi for my lateral area, that gives me, I'm going to go with a different color, 42 pi centimeters squared. Woo! Alright, I like it. I like it. Get rid of that bad boy. So this is an exact answer. Oftentimes in the construction setting, we're going to go ahead and plug that into a calculator, round it, but in the math world, we often leave things exact in terms of pi. 42 pi centimeters squared. Cool. Awesome. America. Alright guys, so these last couple have some weird, strange, crazy formulas. They're not too bad though. Alright, so let's look at this cone. I think we see something familiar here with this cone in that it has a circle base. So base area equals pi r squared. No big deal. We've seen that. We should be comfortable with that. Awesome. But this weird part that wraps around the cone, that thing's strange. Okay. So the lateral area. What we have is called the slant height, which is often drawn with like a cursive L, sometimes with an S. I don't like the S because it looks like a 5 at times. So most people will use this cursive L to notate the slant height. And what we have is pi times R times L. Okay? That gives me my lateral area. On the Google machine, you might see something a little bit different. Okay, you might see square roots of h squared plus r squared. Okay, meaning these guys right here. And that actually comes from the Pythagorean theorem, which we'll learn a little bit later. But what we'll use is this one here, pi r l. Okay, so let's plug some numbers in and work with it real quick. Let's say my radius is 5 and my height is 12. Okay, and actually with our Pythagorean theorem, that's going to mean that our slant height is 13. That's a fun little Pythagorean triple. Again, we'll learn about that later, but why not throw it your way now? Because you love math. You eat it up. It's delicious. Okay, so our base area, pi r squared. Base area equals pi times 5 squared. So that's 25 pi. Awesome. Lateral area. Well, that's going to be pi RL. So pi times my radius times my slant height, 13. Well, 5 times 13 is 65. So it's going to be 65 pi. And you might not have known that, but I did. I'm going to help you out. So my total area, 65 plus 25, that's going to be 90 pi. Units, in this case, squared. Since I didn't put any units, we'll call it units squared. Lovely. Okay, so, not too bad. It's just another formula to remember. We'll jot that down. I'd jot that down in your notes, of course, in your formula sheet. I would jot that all down. It's definitely something to have on hand, especially if you're making some cool, like, hats that are in the shape of a cone. I don't know. Last one we got here, guys, is the sphere. Okay, the sphere is its own special formula. So the surface area of a sphere is equal to 4 pi r squared. That is a super cool formula. I don't think we need to plug numbers into that. Figure it out. If I give you the radius of a sphere, you should be able to figure out the surface area. Okay? Now a hemisphere, if it was half the sphere, hemisphere is just half of it, right? Well, it would be either, if you want 2 pi r squared for a hemisphere, right? Or it could be considered 3 pi r squared. And the only difference here, guys, is if we are including, well, when you slice this sphere in half, you create, you see this guy right here? It's called our great circle. You create this circle base when you slice it in half. So let's say this hemisphere is sitting on the ground. It's creating a dome, right? Well, the hemisphere, excuse me, if you needed to find the surface area of material to make this dome, you would need this one. But say you slice, I don't know, let's say an orange in half. You want to find the surface area of that orange and assume that it's a perfect sphere. You would include that circle base because you created a new face on it. Okay? So there are 2 different formulas for a hemisphere. But again, these are pretty easy formulas to work with. It's the remembering that's tough.